Right, well, good afternoon, good morning, good evening, whatever your time zone to everybody. It's getting on towards the evening here in Pennsylvania. My name is Jonathan Moore, and I've worked for Exida for just over 3 years now. And my background is mostly automotive. I spent many years at Ford Motor Company. I worked for a fairly large tier 1 supplier in the UK, test facility with consulting and safety services. I worked for a startup doing ground-based autonomy for a while, and then came to Exida a few years ago. And mainly my focus has been standards-based software development. I was an expert at Ford in FMEA, and of course I'm now a certified functional safety expert with Exida. You can see a handful of the companies I've worked for there. Some fun with some automation of haul trucks there in northern Utah. In the middle there is a McLaren with a team that I was part of doing climate testing just south of the Arctic Circle in Sweden. And there's a durability truck on the bottom left with an autonomous kit fitted. And on the bottom right, I spent some time in the mining automation space as well. That was a bucket loader that was in the convention center in Las Vegas, to give you an idea of the scale. This is something for you to think about while we go through this presentation. I want you to think about the testing that's going on here. And I'm going to give you 2 data points. The first data point is we did a test with a rifleman, and they took 22 consecutive shots. And what happened was they hit the bullseye every single time, but the conditions were ideal. There was no wind, the sun was behind their back, they were to rest their arms, and they used the same rifle. The test team came back and said, we got another rifleman, and that person took 3 shots throughout a demanding day with some disturbances there, some strong crosswind. The sun was in their eyes, different rifles, and that rifleman hit the bullseye at varying distance. So they didn't hit the bullseye, they missed the bullseye, but they hit the target at varied distances from the bullseye. And what I want you to think about is now you're going to be this person holding the target for the ongoing rifle practice, and you've got no control on when or under what conditions the shots will be taken, but you have to sit there like this gentleman and hold the target. You can select between Rifleman 1 and Rifleman 2, and all you know about them is their demonstrated shooting performance. So this might remind you of some test results you've been asked to make a judgment on in selecting a design. So I want you to select Design 1 Rifleman 1 or Design 2 Rifleman 2 if you were having to sit here under this target. So which rifleman would you select and why? And if you're unsure, that's the distance from the failure mode just there, okay? So think about that, and we'll come back and I'll tell you what my experiences were with the answers to this problem. Exida's got people around the globe to support you with your functional safety, your alarm management, and your cyber security. And generally, we're the people you turn to when you want guidance on these standards. And today I'm going to talk to you about robotics. We are perform about twice as many industrial device certifications to all 3 TUVs combined. TUV have been at Logic Solver a lot longer than us, and we're doing about the same number of certifications as them after they had probably a 20-year head start on us. These are some of the customers I work with and my colleagues work with. You can see towards the top the OEMs, the people who assemble the cars. Their tier 1s are all companies we work with, and we do a lot of work with suppliers to tier 1s, including the basic technology suppliers of the chips and the integrated circuits, the IP and the IC design. People like Texas Instruments and Intel are our customers. Even companies like Synopsys, who generate the tools that you use to create integrated circuits. And of course, there's many, many more companies who we work with. This was created for our 20th anniversary, which was this year. Unfortunately, COVID meant we couldn't have a party, so we're all looking forward to that next year. But you can see lots of organizations who we work with. There's a book for the training course that we offer in functional safety. You can buy this on the website. And this is a very easy read. Has all the templates, all the guidance you need in order to achieve a development process that is compliant with SIL 3. We've also got books on other areas of reliability and safety in particular. The most recent one is Functional Safety for Managers. That's a very gentle, easy to read overview and introduction. And the Safety of Instrumented System Design is the next most recent book, with some very accessible mathematics that underpin the reliability of electronic systems. Perhaps the biggest contribution exida has made to state of the art is the Safety Equipment Reliability Handbook. These are not published in book form anymore. We have tools with the data in them for you to access for your designs and your parts. Pretty well every component you're going to consider in robotics for safety has a profile in those reliability handbooks there. So we know what the failure modes are, we know what the failure rates are likely to be in the distribution, and we can help you use those parts correctly and reliably to achieve your safety functions. We've got a very poor track record when it comes to safety in the process industry. Approximately every 18 months we have a catastrophic event with the deaths of many people who come to work and don't make it home at the end of the day. And that's a terrible burden we bear in the world of safety. You probably remember the social media videos of Tianjin. That was in 2015, and most recently Beirut had this catastrophic explosion next to the port area there. These are failures of the process industry when it comes to safety. And if history is to be believed, then robotics won't be any different from that, and we have the potential to cause lots of harm. Automotive isn't immune from this kind of thing. Toyota had to pay just over $1 billion there because of a case of unintended self-acceleration. Typically, the argument would be that the driver was not paying attention or chose to press the wrong pedal. But of course, as more and more drivers started to suffer this problem, people realized that it might be something more fundamentally wrong with the vehicle. And crucially in this case, from a software engineering point of view, a bug was not found by the plaintiff. They didn't review the code and say, here's a flaw. They simply looked at the work that had been done by Toyota, and they made the argument that the code was of insufficient quality, so there must be a bug present. And there was a fine and a fair amount of work for exida when we were asked by Toyota to come and assist them with the actions to deal with that lawsuit and the effects of that in their organization. Tesla had a problem with batteries. This was something that we ended up working with the battery supplier on. Happy to say that problem's been largely resolved. And you might remember that Takata went out of business. Here are the three guys testifying in front of the US Congress. They filed for bankruptcy, and not only were there several fatalities all over the world, but there was a significant impact to the supply chain as automotive OEMs had to find an alternate airbag supplier. Uber had a high-profile incident with their software set to ignore objects on the road, and you might remember Nightscope here, a robot that decided to commit suicide. I don't know what the word for that is. I don't know what the word for robot suicide is. Roboticide, maybe. I don't know. But obviously, they'd not anticipated the use in the shopping mall with the steps down to the pool, and it had gone and taken a tumble there. Airline industry, these are things you can look at in your leisure on Wikipedia. The turbofan there was due to impurities in the metal, and it ruptured all 3 hydraulic systems, resulting in 111 deaths. And you'd think that with 3 hydraulic systems we had sufficient redundancy. Well, of course, if you have a single point of failure which ruptures all 3 simultaneously, you've defeated your reliability, of course. The Ariane had a number of problems in their inertial navigation. That was a fairly significant loss, and the explosion there. And we make mistakes with mechanical design as well. Have a Google for the Hyatt walkway collapse, an unchecked design, a schoolboy error in the assembly, 114 deaths as a result of that as the platform collapsed on the people below. What do all these things have in common then? Well, somebody went to hospital, and in many cases the organization responsible had their reputation damaged. If you think of a hospital as a general purpose system for resolving the effects of harm, sometimes they're successful, and you go into hospital and you come out in better shape than you went in. And of course, there are people who don't make it out of hospital because they die. So hospital is very good at dealing with many of the reasons that we get hurt. And of course, electronics and engineering systems, we are steadily finding more and more ways that we can hurt people. And the reason we hurt people is because the products were launched with missing features, or because the failure rate was unacceptably high. Or we knew there were faults and bugs and defects and opportunities to improve, but we didn't make them. So think about this. What stops your product launch following this trend? What's stopping your company making a catastrophic error that leads to an event about every 18 months in the world? Does your company launch with missing features, with a failure rate that's too high, with faults and bugs present? And is any of that safety related? And how do you know whether it is safety related? So do you know which features are missing? Do you know what your failure rate is? Do you have a bug list? Do you know which of those bugs are safety related? And whether somebody has examined that to make sure that it's still acceptable to release that design into production. Here's some examples from my career. I was fortunate to see the underside of this haul truck here. This haul truck's in Utah. This was in the mine. I wouldn't recommend this as the way to conduct an inspection of the underside of the truck. You can see from these photos what happened. There's a dump pile here on the left. The spacing was too close together, and the truck drove over part of the previous dump pile, and once it reached the tipping point, it was too heavy to hold itself and dumped to the side instead of behind. There's a truck in the ditch. We failed to anticipate this might happen, and that was a reasonably expensive repair, but of course we lost some testing time because we had to go and recover the vehicle. You need to know that there are organizations in the world who are searching for liability lawsuits. This is an example of a website of a legal firm. They have a picture there of an aftermarket modification to vans. They identify the names of the companies making those vans in red. And even the lawyers realize that safety arises when an aftermarket manufacturer modifies the vehicle. These companies do not do testing and do not have adequate engineering teams. When these vehicles are modified, the fuel system, the seats, and other critically important safety components of the vehicle will be modified without adequate safety testing. Please get in touch with us to begin your lawsuit against these organizations. So the world of liability is quite challenging. People are out to find products that are unsafe. And so this is some advice that I was given the early days of my career at Ford, the company generates many documents, and the documents may have to be provided outside of the organization to the media or government agencies or used in court. So it's important to remember the effect what you communicate can have on the company. And we communicate in many different ways today. And I listed a few here to be explicit. All of these means of communication can potentially go outside of the organization and not be private. And certainly in the case of a lawsuit, will be subpoenaed, and the discovery process will allow the plaintiff to get access to those records. So we got some guidelines for communicating. Think about the medium. Certainly debating issues is best done in person on a phone call. That's not to say we want to hide information, but if we're not discussing facts and we're not looking at data that supports conclusions that we need to make, debates are best had in discussions and in phone call, and then record the results of the debate rather than the things we might regret saying in a heated debate. Consider who you're sending it to, be factual, specific, and accurate, obviously. And I was advised to avoid emotional words and exaggerations, not to draw conclusions unless I was required to, and stick to facts. Make sure I don't speculate, especially if I'm not the decision maker. These are general guidance from a large organization which is used to dealing with ongoing lawsuits. All makes sense to me. Think about protecting your company and reputation. It's important that you identify issues and help solve them. I had a manager, and I was told many times, thank you for raising the issue, but that's only 50% of the job you're paid to do. I need you to do the other 50%, which is to resolve them. And she was very consistent with that advice to me, and I'm happy to say supported me when we needed to resolve issues. So direct issues to the people responsible and make sure you include all the context and the detail to act. And the crucial thing is to close the loop on issues. Once they're raised, make sure they don't fall off the table. Hopefully you've got a system for recording them. Make sure you don't leave out the good works and the results of closing issues. If in discovery, all the engineers and the people reviewing your work see as issues being raised and no evidence that you're closing them out, it paints a very different picture from routinely raising issues and closing issues regularly. So ask yourself, would you want to explain what's written in your email or your document to someone conducting an investigation? Would you want it on the front page of a morning newspaper? And if not, then you need to think about a different way of communicating that information or modifying that document so you do tell the whole story, so that you would be happy to do that. I'm sure in the case of Uber's early days, these two guys wish that these words that they'd recorded in I think this was a social media tweet, wish that this had not, wish they hadn't written this, or wish they'd said this to each other rather than recorded it. And of course it wasn't found on his phone, it was found on someone else's phone, but all part of the discovery phase, and all used to paint a picture of the reputation of these individuals that were accused of stealing trade secrets. So it does make the front page in many cases. I call this the incompetent, ignorant, and lazy slide. So quick summary of the world you're in if you're in safety engineering or making robots that work in close proximity to people. If you do hurt somebody and they go to hospital, then you may find a claim. And the claim will go to a court, because a court is the place we go to in order to resolve accidents. And sorry, not accidents, arguments. A court is a place we go to resolve arguments. So a plaintiff will come to the judge and say, I don't think the product was safe enough, that's why I got hurt, or that's why my loved one was hurt or killed. And you now have to build an argument to say the product was sufficiently safe, and the court will decide who's correct. They'll start with a substantial evidence test, which means they'll make sure that there is evidence to support the conclusion, in the case of the plaintiff, the conclusion that the product is insufficiently safe. And I want to see a reasonable connection between the facts on record and the choices that were made by the engineers, especially looking at the reports with facts that are contrary to the conclusion the product was safe. We'll then do the arbitrary capricious standard, which is the good hard look, to make sure that you considered all the important aspects of the problem, whether there's an explanation that runs counter to the evidence. It'll ask things like whether the engineers and the developers had the expertise needed to develop the project. How would you justify and demonstrate to a court that you had the skills and expertise to do your job? And that will go in front of an expert witness who will be asked to give an opinion on whether there are sufficient facts and data, whether the conclusions are the product of reliable methods and principles, and whether these principles and methods have been reliably applied. So if you're not using reliable methods, you're going to fail that test. And if you're trying to use reliable methods, but you've used them incorrectly, an expert witness will point that out. So it might make sense to get the expert involved beforehand. And then finally, none of these standards ask whether the conclusion you came to was correct. So nobody's going to ask whether the risk reduction was achieved, whether sufficient risk reduction was achieved. They're going to ask whether the approach you used was reasonable, whether the information provided and you used, the safety case was reasonable, and whether the analysis at its core was reasonable. That's what they're going to ask for. And that word reasonable is often very difficult for engineers because we trained as engineers and we like mathematics and certainty and numbers and values. And reasonable is not something we can assign a value to. But this is the area the court works in. They're going to look at whether our argument for safety was reasonable. And so that's our objective in safety engineering. So what is safety all about then? Well, there's the three pillars. We've got to avoid what are called systematic faults. So these are faults that arise because we are human and we make mistakes and we don't do things we should do and we get distracted. And so these are systematic faults that can occur during design and development and production. We can have those faults present themselves during operation, and our job there as safety engineers is to anticipate them, detect and control them. And we know that we can get faults during operation because the parts are different. They're being subject to different environmental conditions, and there is randomness in their behavior. And there are faults that can occur randomly because of disturbances from the environment. In case of electronics, that might be heat and vibration. It might be electromagnetic waves. It might be high energy particles from the solar system that can cause our very tiny electronic circuits to be disturbed. So typically things we do for systematic faults include looking at the documentation, wants to review it, wants to inspect it, making sure we write correct code, not overstressing hardware parts. These are all things we can do to anticipate those faults and minimize the chances of us being affected by them. We can detect and control faults during an operation by adding supervisory features into our hardware and software, so we can detect faults as they occur and maybe choose a different result. For the hardware random failures, typically we're adding diagnostics and switch off paths to independent of the diagnosed parts so that we've got continuity of function. So they're the three pillars of functional safety. Avoiding mistakes that we make as humans in our design and development, anticipating them, detecting and controlling them, and anticipating random hardware faults and detecting and controlling them. That represents the state-of-the-art approach today. So what is state-of-the-art? Well, you've got a sliding scale. If you've got old technology and things that have been done before, pretty well you can go and find a standard from the various catalogs, and you're going to find a performance-based standard that's already been written by people that have done that work, and really all you have to do is pick up the standard and do as you're told. As you get more complex and you start to get into the realm of things that have never been done before, you're a startup and you're a disruptor, and you're bringing together electronics in a way that's never been done before, you might not find a standard, and you want to work your way down this list. So for the simple stuff, 61508 Part 1 and 2 and 13849 RIA have a number of performance-based standards that are helpful for fixed position robots. You get into the realm of PLCs and slightly more complex microcontrollers, you might use 62061. If you get into complex electronics, then if you're on an automobile, you'll be looking at ISO 26262 and the SOTIF standard 21448. But for everything else, you'll be looking at 61508 for your complex electronics. So if you're using microprocessors with complex programming languages, maybe multiple cores, then 61508 is the right standard for you to be looking at. The other standards don't really help you. As an example, a technician was inspecting this machinery here, and the robot moved and hit the head, and he was crushed to death. And the lawsuit said a failure of one or more of the dependent safety systems had taken place, causing death. The automated safety systems did not work as it should have. The safety doors meant to stop the robot's movement failed. So how would you approach a problem space as complicated this and make sure that you had sufficient safety there so that you weren't responsible for this person not going home at the end of a working day? Well, in the US, you don't get a lot of guidance in law. The US is traditionally has a very low legal requirement for product sales. We know that it is the threat of liability that drives standards and standardization in the US. It's different in different parts of the world. I'd be happy to talk to you if you're in a different part of the world, how it works in your country. But in the US, the legislation is developed at a federal level. Here are the key agencies. We know that the FCC requires us to do some level of interference testing. Functional safety doesn't really come under the OSHA area, but it's about the closest we might get. So if we're going to do something in the case of the US, it's not going to be the law that's going to demand that. It's going to be the threat of litigation that requires us to use state of the art. Functional safety is not the same as OSHA. A lot of people new to functional safety, particularly in robotics, get confused by this. OSHA is concerned with the health of people in the workplace. So there's this nice balance between what employers must do, what your company must do, and what you must do legally, what you must do when you start working for a company. So your employer have got to provide you with a safe place to work, not ask you to do something that's unsafe, give you the protective equipment that you need to do the tasks, and they've got to allow you to report concerns, and crucially, without fear of losing your job or being punished for that. There can be no recourse for reporting concerns. Your role as an employee, again, legally, is to maintain a safe workplace, not to cause unsafe conditions, make use of the equipment that's provided, and to report safety concerns. So if you see a colleague doing something unsafe, it's your responsibility to go and talk to them and ask them to stop what they're doing until it can be confirmed that what they're doing is safe. If you are given safety equipment, you must use it. And if you leave a mess after you've done your work and it causes an unsafe condition, you've got a responsibility to make sure that gets cleaned up before others suffer from that. There's a nice balance there between the employer and the employee, as you would expect. It's really together the only way we can achieve safety in the workplace. It's very different from functional safety. This is making sure products can be operated safely, making sure that when a product does fail or is about to fail, that there's adequate warning and a safe state gets achieved. And to do that, we have to make sure that any risks that are present in the product are reduced to a level that is broadly acceptable to society. And again, that is not a very engineering definition. Broadly acceptable to society is not a constant. There is no equation for that. So we have to collect the evidence and construct an argument to prove all of this. And what I'd ask you to think about, when was the last time you made a mistake? And hopefully everyone's humble enough to realize that we make mistakes all the time. And so we should plan for that and include that in our safety culture. We have a technical definition of risk. This is in a standard called ISO 12100. And we're expected to look at the hazards that we might cause in the use of our product. And we're expected to assess it on a scale of severity and a scale of probability that the hazardous situation might arise. So we might say the severity is in the middle there, that's the severity, and that there's a probability of the hazard being present and someone being exposed to it. And what we might find is that point there is above the tolerable risk margin, and that we can't accept that risk for our product. So that means we have to reduce that risk with things like separation controls maybe, or training, or labeling, depends on the risk. But we still may not achieve enough risk reduction, and typically in robotics that's the case, and we have to add additional risk reduction, which is going to be the responsibility of our electronics. And the amount of risk reduction we need to get to the lower than tolerable risk is measured on a scale, either a safety integrity level or an automotive safety integrity level, and that tells us how much risk reduction we need and how much rigor we need in our process. And of course, there's some obvious conundrums here. If you take driving to work or driving a car, obviously the severity of driving a car is very severe. You can die, you can kill all the people in the car with you, and you can kill all the people in another car or pedestrians, so you can have multiple fatalities. So the severity of hazards associated with cars is quite high. And we do it all day, every day. We're always exposed to that while we're driving a car. We could have an accident. So that would be on the top right there, and yet society accepts that risk because the individual probabilities of that are quite low. About one significant incident every 2 million miles. But 100 people a day die on the roads in North America. And we accept that level of risk. A stab to the heart, that would be quite severe, but the probability of that's probably quite low. You know, to contrast that with that same knife cutting you 1,000 times, well, a single cut is fairly negligible, but by the time you've had 1,000 cuts, you're probably going to be suffering, and you might even die from that. So you might have death by 1,000 cuts on the top left there. So that's risk reduction in a nutshell. So what does the safety integrity level mean? Well, it's got implications for the systematic capability. So the things that we do in our design process need a level of rigor. The higher the SIL is on a scale of 1 to 4, the more rigorous is needed. So if you're a SIL 4 risk, then you need more rigorous methods than a SIL 1 risk. And that's nice, because what that says is we don't need to do the most difficult, most time-consuming, painstaking engineering on everything. We can scale the effort that we put into safety to the level of risk and have a response that's commensurate to that. And the methods in the systematic capability guidance are wide-ranging. They may range from single decisions, which you can make immediately, things like the programming language that you're going to use. They may be individual activities, things you're responsible for, your own competence, things like that. They may be activities that take that require a sustained team effort, and there are methods for systematic capability that require specialist knowledge and specialist tasks. Tasks using methods and principles that maybe your team, maybe your company doesn't have experience with. On the random failure side, it's a little bit easier. the sill tells us what the probability of failure is that we're allowed. The higher the sill, the lower the probability of failure. The lower the probability of failure. And there are fewer methods here. Typically, we want to be using fewer components for the safety system, using better components that are over-engineered, improving the environment. We might use redundancy and fault tolerance, and we're certainly going to be doing things like diagnostics and preventative and corrective maintenance. These are techniques we use to reduce the random failures of our parts. So they're complex in their own right, but the methods for the random failures are fewer than the methods for the systematic capability, as you'd expect. So what is tolerable risk? Well, here's a definition from some work performed by the HSE, and this is pretty well accepted worldwide now. Tolerable risk is about a probability of a failure causing death, one chance in a million per year. And that's on a level with the chances of being struck by lightning or getting bitten by a snake or dying in an airline crash. That's considered the broadly acceptable region. And is that reasonable? Well, if you heard thunder, would you continue to lean against a concrete wall or against a light post? So even if it's a concrete light post, likely it's got a metal reinforced rod down the middle of it. Would you pick up a pipe or a tap or a faucet, or go and stand next to some metal fencing? Would you go and stand on top of your truck? Would you go swimming or jump in a boat quickly if you heard thunder? Would you carry on playing golf? Would you fly a kite like our friend Mr. Franklin here was lucky to survive? More than likely you wouldn't. If you heard thunder, you would look at your smartphone to see what was going on, but you would seek cover, because the consequences of being hit by lightning are fairly severe, and it's very easy to avoid that by going indoors. So that's roughly where that level of risk comes from as a society. Obviously, we as a society can change our level of risk. We might find this new generation is more risk-taking than us, and maybe they will go and stand outside in the thunder. I don't know. But the goal is to reduce the level of risk to an acceptable level that society considers acceptable. And to prove that, you might come to an organisation like Exida to get a certificate. This is a third-party attestation that you've done the activities necessary to prove that your design is sufficiently safe. And we are governed by an ISO IEC standard that has requirements placed on us as a body that operates a certification program. And it means we get a certificate from ANSI every year after an audit, and we have to maintain this if we want to be an accreditation body. And as part of that process, the certification body, Exida, must use a scheme, and the scheme is what we use to detail all of the certification requirements, including the interpretation of standards. Problem with standards is they're a snapshot at a point in time, and as the standard gets older and older, state of the art changes and deviates from the standard. And oftentimes we find that the standard is wrong. There are errors in the standard. There are mistakes in the standard. And at Exida, we publish our scheme and our interpretation up front, so you can see that. And where we disagree with the standard, or where we think the standard is wrong, we subject ourselves to a requirement that we publish our position, our interpretation in 2 reputable journals which are peer-reviewed. And again, all of that information is on our website. You can see the parts of the standard, how we interpret it, and where we deviate from the standard because it's wrong. We've found that we've learned since that the standard is inadequate. So it's well known then that the Exida scheme has added requirements beyond what's required in the standard. We have nearly 400 billion hours of operating hours of field failure data with which to use to identify the failure rates and the failure modes. of all of the components that you'll be using in your robotics projects. Typically, the manufacturers of those components that you're using will have worked with us for some time before you decide to use them. And we publish the failure rates, not just the PFD average. We do analysis of their field failure data to confirm our failure rates. And there's a number of other activities we perform with the owners of these components to make sure that we understand them fully when it comes to using them in your robotics projects. And it's well known that the exida scheme is the toughest technical requirements of any certification body. And of course, that's what people want in the world of safety. They don't want a wishy-washy certification. They want to be held to the highest standard because we're talking about people's lives. Here's how a project might work. In principle, all you need to do is submit your safety case. We audit that, check the requirements are met, and issue a certificate. But typically, you need some help developing the safety case. So we start out with a gap analysis. That might require some training. The gap analysis takes a day or two, and we can give you a good indication of what it's going to take to certify your project. Typically, the activities on the right are going to be performed by you because most people know how to do planning and requirements and software development processes and things like that. The specialist activities on the left, the FMEA, the FMEDA, these are things that you might want to get some help with exida. And the gap analysis identifies what's missing, if there are any gaps, and we can help you plan and cost the activities to close all of those gaps and get you a safety case. So typically in a robotics project, you might have a few hundred hazards. I've done many of these, and I think there was a project where we had 550 hazards that were analysed. But typically that boils down to about a few hundred mitigations. 50 of those might be complex electronics, and we might have 10 safety goals associated with that. And typically in robotics, we'll get a remote e-stop safety goal. We need to be able to stop the machine without, we're not sat on the machine or near it, so we need to have a remote capability to stop it. More than likely there'll be some speed control safety goals, and if the machine is moving near to people, then we might need to deal with separation controls, and that could be as simple as obstacle detection, but it might also be obstacle avoidance, which gets a little bit more complicated, of course. And then after that, the safety goals become very product specific. So I need to know whether you're high speed and high energy or low speed, and whether you're operating among the general public or in an industrial environment in order to go through that. But that's a typical outcome of the hazard analysis. And each of those safety goals, of course, will attract a safety integrity level, and from there, the rigor and the methods need to be applied. So what can you do? Well, you can put a tick next to taking the time to inform yourself. It's a good idea to come and listen to this seminar. What I'd suggest you do is start asking more questions. So contact me. By all means, take the time to find out whether there is a safety team in your organization. You might find there are some people who have been through this previously in your own organization. But if not, reach out and ask your questions. Think about the hazards and the mitigations, and look at the test results for your product yourself, and inform yourself what are the dangerous failure modes of your product. If you are working in a safety-related environment, then you should be following a procedure in everything you do related to safety. And if there isn't a documented process for the work you're doing, then you might want to raise your hand up and suggest that one gets created, or help create one yourself. Share your concerns, document the resolution to those concerns. That's crucial. And you might consider getting a professional certification from exida. So we offer a certified functional safety accreditation. You can apply for that and take the exam and call yourself a functional safety expert. Things you can do is to join your professional societies. And if there isn't a professional society for your particular product space, consider starting a trade group with your competitors. and establish a minimum standard for your particular domain. In ISO 9001, typically we ask people to say what they do and do what they say. When it comes to liability and safety, we ask people to say what they mean and to mean what they say, as a way of thinking about the work that you're doing. And if you aren't able to articulate your safety argument for your product in words that your family can understand, you might want to raise your hand and ask how your organization is protecting itself against the possible litigation if there is a failure and somebody gets hurt. Here's a section of ISO 26262. It's in part 2, the management section. This is Annex B, and on the left are some leading indicators of a poor safety culture, and on the right are examples we've found that are present in organizations that have a good safety culture. What I challenge you to do is read through a few of these and score yourself. It's always easier to score other people or other departments or other companies, but try scoring yourself and ask yourself, over the last week or last month, did you exhibit any of the characteristics on the left? And if you did, pick one or more of them and set yourself an objective to change that behavior, so that 6 months from now, when you make an assessment of yourself, you're more on the right-hand side of this chart. You can't change yourself, you're going to struggle to change those people around you. And that's what we want from safety engineers. We want you to influence the people around you towards a good safety culture. If you still want more information, please feel free to email me. If I can respond in a few sentences, I will. And if it's a bit more involved in that, then I may be asking you to think about a consulting engagement. But I'm more than happy to answer questions, phone call or email, whatever suits you. You can always use our website. There's the resources section shown here. This webinar will be online shortly for you to listen to it again. There's white papers and case studies, and there's plenty of information in there for you to help yourself too. So back to our friend in, I think it's North Korea. Rifleman 1, Rifleman number 2, you've got to hold the target. Which one are you going to pick? The vast majority of management pick number 1. And there are a handful of engineers that recognize that Rifleman 2 is the one that you want. Because at least you know that Rifleman 2 can deal with these conditions. You have no information about Rifleman 1. And so you've no idea what will happen to that rifleman when you're under the target, when the wind might be blowing and the sun might be in their eyes. So in all cases, it's much better to pick the design that has been tested and stressed with representative disturbances, even if the sample size is a lot less. The point is that the confidence in your data is not a function of sample size. It's a function of noise factors. There's training courses that you might consider, and I think all of these now are online. Certainly the automotive ones are. It'll be me that you're listening to there, and I'll gladly talk to you as you're watching the videos if you find that helpful. We give you 60 days access online, and you can listen to those at your leisure. There's an exam that's optional that you can take at the end if you want a certificate of competence, and you can pass that exam. There's some upcoming courses that are already scheduled, so you can join those to participate with other students. And if you want more information, we're in all the usual locations, and there's my email address again, and some more website links for you to look at. Now, I think at this time I have to look through the questions. And let's have a look. How do I widen this out? Let's have a look. So the first question, is a recording going to be available? Yes, there will be a recording available. You'll get an email with the link to that on YouTube. Isn't still applicable to chemical processes and machine safety applicable to robots? Well, SIL is applicable to all electronics performing safety functions, regardless of whether they're the safety industry or the robotics industry. There we go, somebody's left. Okay, so thanks for your questions. And like I say, if you've got more questions that you'd like to ask privately, please send me an email. Kristen, did I miss anything? Now I'm worried nobody's been able to hear me for the last hour, but anyway, let's hope not. Well, Kristen, if I've not missed anything, I think we're gonna call it there. Thanks everyone, and I look forward to hearing from you.